Good morning, children. Today we will study ionization enthalpy or energy or potential in detail. That day we had seen what is ionization energy. It is the amount of energy required to remove the most loosely bound electron of an atom in its neutral isolated gaseous state and convert that into an ion. Now, which ion? Obviously, a cation. So, what is the amount of energy required to pull out the most loosely bound electron of an atom in its neutral isolated gaseous state such that it gets converted into a cation. So, any metallic any metal in the gaseous form, you provide energy, ionization enthalpy, it gets converted into a cation and electron is removed. Now children, trends we had seen in a group, top to bottom it decreases, so arrow is upwards. Above elements have higher value and the lower ones have got lower value. So in a group, top to bottom it decreases. In a period left to right, it increases. This was taught to you in the last class. Then children, we have to see today the factors affecting the value of ionization potential. First factor is size of an atom. It is inversely proportional to size. Inversely proportional. How? Bigger size, effective force of attraction of the nucleus on the valence electrons will be lesser, hence they can be easily pulled out and we require lesser energy, hence IE will be lower. So size of an atom, it is inversely proportional, and this was taught to you even in class 10, so you know it from there. So bigger the size, lower the value, smaller the size, higher the value. So it is simply inversely proportional. Then comes nuclear charge. Children, higher the nuclear charge, it will be difficult to pull out electron, hence more energy will be required, more will be the value of IE. So nuclear charge, it is directly proportional. Simply directly proportional to nuclear charge. Higher the nuclear charge, greater will be the IE. Third factor is neutral. This we have to take up in detail. It is called a screening effect or shielding effect. Children, these 2 points were very much known to you, size and nuclear charge. This is the third point and important and new for us. Children, I'll explain you what is this screening effect or shielding effect. Now, consider those atoms which have got a large number of electrons in them, especially where the number of electrons in the inner shells is much higher than the electrons in the outermost shell. Say talk of your transition metals, D block metals, 4s1, 4s2, but D can be 1 to 10, any number. So suppose we have an atom, it is a nucleus where it is neutrons and protons, and there's a first shell which must be having 2 electrons, you know very well, it must be having 2 electrons. There is a second shell, it can have 8 electrons and they must be there. Third shell, it has S you can have 2, it can have P will have 6, and D any number from 1 to 10. So children, and here it is just 4s, which is either 4s1 or 4s2. So those atoms where we have large number of inner electrons, it is seen that those inner electrons, they act as a shield or screen for the electrons of the outermost shell. They act as a shield or screen for the electrons of the outermost shell. Hence, they experience lesser effective force of attraction of the nucleus on them. Hence, those electrons of the valence shell in those cases can be easily taken out. They require lesser energy and thus they have low IE values. So what is the screening effect? In those atoms where the number of electrons in the inner shells is much higher than the electrons in the outermost shell, it is seen that the electrons of the inner shell, they act as a shield or screen for the electrons of the outermost shell, due to which these outermost shell electrons, valence shell electrons, experience less effective force of attraction of the nucleus on them as compared to the expected value. This effect is known as shielding effect or screening effect. Due to this, the value of IE, ionization energy or ionization enthalpy, gets lowered. So, a screening effect, it is inversely proportional to IE, because the screening effect or shielding effect, children, since this shields these valence shell electrons, hence they can be easily taken out, because this force of attraction of the nucleus which was expected is not actually that much effective there. So they experience weaker or lesser effective force of attraction of the nucleus on them, and this, due to this, IP value lowers down because we require lesser energy to take out electron. Suppose this is the effective nuclear charge, say Z star, and this is the nuclear charge. Nuclear charge means what? Atomic number. And suppose this is your screening constant or shielding constant. So what will be the value of this effective nucleus force of attraction? Obviously lesser than the expected as per your atomic number which was expected, and higher the value of this screening effect or shielding effect, lower will be the value of this effective force of attraction, and lower the value of effective force of attraction, obviously those will be requiring lesser energy for the electrons to be pulled out, right? And hence the value of IE will be lowered. So I hope you understood the concept of a screening effect. In the atoms where the number of electrons is much higher than the outermost shells, means those atoms where we have large number of electrons in the inner shells, those electrons of the inner shells shield or screen the electrons of the valence shell, due to which the electrons of those outermost shell, valence shell, experience lesser or weaker effective force of attraction of the nucleus on them. Hence, we require lesser energy for them to pull out electrons. This effect was known as screening effect or shielding effect. Due to this, the value of IE goes down. So screening effect or shielding effect, it is inversely proportional. Then children comes penetration effect. Suppose we have fourth shell and electrons taken out from S, P, D or F. So S being closest, you require greatest energy. If the electron has to be taken from P, naturally as compared to S, P is not that strongly, tightly held. Then D is further far and F is farthest. So as we move away from the nucleus, effective force of attraction of the nucleus on those shells and the electrons present in those shells becomes weaker and weaker, and thus they require lesser energy. So if it is the same shell, suppose fourth, so S requires highest energy and F the least. So for S the value will be highest and for F it will be the least. This will be the order. Then there's one more factor, electronic configuration. I would say one of the most important factor. This I will take up, children, in my next video, because this requires time and a thing which involves many other points also while explaining this. So I hope as per size it is inversely proportional. Nuclear charge, it increases, IE increases. What is shielding effect, you have understood, and it is inversely proportional to shielding effect, because higher the shielding effect, lesser will be the effective force of attraction and lesser will be the IE value. And what is screening effect, I have told you. So for this video I stop here. In my next video I'll take up electronic configuration, this point in detail. So I stop here. I hope points are clear to you. Thank you, children.